In this video, we'll be talking about intramolecular forces and potential energy in ionic bonds. Remember, the prefix intra means inside or within, so these are the forces between the atoms in a compound. We'll also be talking about ionic solids, how they're put together, and some of their special properties. You'll remember that in ionic bonding, one atom loses valence electrons and another atom gains them. The ions that lose electrons are usually metals, and the ions that gain electrons are nonmetals. Atoms that lose electrons become positively charged cations. Atoms that gain electrons become negatively charged anions. The opposite charges attract each other. But it's not simply a 1-to-1 or 1-to-2 or 1-to-3 relationship. Ionic compounds tend to form three-dimensional lattices when they're in solid form. These are large, organized crystalline structures where each ion is surrounded by a bunch of other ions of opposite charge in a definite pattern. Here's an example. This is a representation of the three-dimensional crystal structure of sodium chloride. The purple spheres represent sodium ions, and the green ones represent the chloride ions. The ions are packed together in a way that maximizes attractions and minimizes repulsions, and to provide these ions with the most stability. And for the sake of packing, these ions behave a lot like spheres. So when we construct our models, we can think of the ions as spheres just to help us understand what's going on. In sodium chloride, every sodium ion is surrounded by 6 chloride ions, and every chloride ion is surrounded by 6 sodium ions. In short, each of the ions is attracted to 6 other ions with opposite charges. This makes these compounds very strong. Lattice structures will be different depending on the ratio of one ion to another ion in the compound. The relative sizes of the ions involved will also affect the structure. Compare these two pictures. You can see that the ions in these compounds have different relative sizes, and the structures are also different. Even though you have this lattice arrangement where one ion is surrounded by other ions with opposite charges, these compounds are neutral. The charges are always balanced. Ionic compounds are held together by electrostatic forces, and these are governed by Coulomb's law. The strength of an ionic bond depends on the magnitude of the charges on the ions. For example, whether there's a 1+ charge or a 2+ charge or a 3+ charge, and we can see this with the Coulomb's law equation. The larger the charges, the larger our numerator, and the greater the force. And you can see how these charges multiply in the sodium chloride compound. Sodium and chloride both have a charge of 1, and in the Coulomb's law equation we multiply the charges. 1 times 1 equals 1. In magnesium oxide, the magnesium cation has a 2+ charge, and the oxide anion has a 2- charge. When we multiply these by each other, this increases the numerator in our Coulomb's law equation by 4-fold compared to sodium chloride. The distance between the centers of the ions when they're packed to form a crystal also affects the force. From Coulomb's law, you can see that the force is inversely related to the square of the distance. The farther apart the nuclei are between the two atoms, the weaker the force. However, when we're talking about ionic compounds, because the atoms are so close anyway, it's the magnitude of the charge that's going to make the greatest difference in the amount of force. Now let's talk about energy, which is very closely related to force. Energy is important when you're talking about the formation of ionic compounds. It's also related to the forces that combine to pull these ions together and to the strength of the ionic bond. You can get an estimate of the strength of the bonds in ionic compounds by measuring the lattice energy. This is the energy that's given off when oppositely charged ions in the gas phase combine to form a solid. When two oppositely charged particles come together, energy is released as they come together. The ions want to come together, and this reaction is exothermic. Often, it's really exothermic. When you have oppositely charged ions, being in a lattice is energetically favorable for them. It makes them stable. So, ionic bonding is all about energy. The lattice energies between ions with smaller radii are much larger than the lattice energies between ions with larger radii. This is illustrated in this table. You can see that the lattice energy for the lithium and fluoride ionic compound is very large. It's 1036 kilojoules per mole. These two ions have small atomic radii. Now let's look down lower in the table. The lattice energy for the cesium and iodine compound is much smaller at 604 kilojoules per mole. These ions have larger atomic radii. Keep this in mind when we work problems later. Now let's talk about the properties of ionic compounds, since these have to do a lot with the structures of these compounds. Ionic compounds are very strong. Moving ions out of the lattice is very hard to do. It disrupts the structure. Ionic compounds have an ordered crystal arrangement. This makes sense when you think of the lattice structure, which tends to have a very regular geometry. Ionic compounds tend to be very brittle. You can't bend them. Breaking causes the ions to shift relative to each other. They break along cleavage planes. Ionic compounds do not conduct electricity when they're in the solid state because the ions aren't free to move around the lattice. However, ionic compounds can conduct electricity if you dissolve them in a polar solvent like water. Ionic compounds can also conduct electricity if they are molten or melted. The positive and negative ions can move around freely, and this can cause an electric current. In fact, one test to see if a compound is ionic is to drop it in water and dissolve it and see if you can get electricity to go through the solution. The more ions in the compound, the more moles you get when you dissolve them, and the larger the current you get when you pass electricity through the solution. Ionic compounds have a very high melting point. The attractions between the cations and anions in the lattice are very strong. It requires a large amount of energy to break all the bonds in the crystal. For example, sodium chloride has a melting point of about 800 degrees Celsius. These properties of ionic compounds are related to the lattice structure and the strong bonding. One type of problem you may see is one that involves melting points. You may be given different compounds, ionic or covalent, and you may be asked which one has the highest melting point. If you see one of these problems, here are some things to think about. Ionic compounds have a higher melting point than the covalent ones. Remember, if you have a compound between a metal and a nonmetal, it's probably ionic, so that's one strategy you can use to figure these problems out. Another is to look at the charges. Remember, ions that have higher charges have stronger ionic bonds than those with lower charges. They're harder to break, so these compounds are harder to melt. If you're looking at compounds where all the ions have the same charge, size is important. Ions with smaller atomic radii that form bonds have higher lattice energies and stronger bonds than compounds that are formed with atoms that have larger radii. Hence, the compounds formed with ions that have small radii tend to have higher melting points than compounds with ions that have larger radii. You can see this in this table. The ionic radii of sodium and fluoride are smaller than those of other ions. These ions are packed more closely together in the lattice. Sodium fluoride has a higher melting point than potassium fluoride or rubidium fluoride or cesium fluoride. These have cations with larger radii. Now, I want to end this video with two video clips. The first is a classic reaction between sodium metal and chloride gas. As you can see, the reaction was very exothermic. Exothermic enough to cause a lot of light and a lot of heat. Now let's look at another reaction involving magnesium and oxygen. Each of the ions formed will have a larger charge, 2+ for magnesium and 2- for oxygen, compared to sodium chloride, where the charges are 1+ and 1-. The Coulomb attraction for magnesium oxide is larger than it is for sodium chloride, and we would predict the energy released when these ions combine to be larger too. Let's look at the reaction. We can see that there's a lot of energy released in the form of light, and if you were close to it, you'd feel the heat as well. Although it's hard to quantify the amount of energy released based on just watching a demonstration, we can see that the magnesium-oxygen reaction is very impressive. So now you should know about ionic bonding. You should be able to explain how Coulomb's law can be used to understand the strength of the interactions between anions and cations, and how strength relates to the charge on each ion and the size of the ionic radii. You should be able to explain how the anions and cations in ionic crystals are arranged in 3D lattices to minimize repulsive forces. You should also be able to describe properties of ionic compounds and make predictions about lattice energy, melting point, and other properties.